Hi guys, welcome to lesson 7.5 on applying properties of logarithms. We're going to be using some of the properties of logarithms during this section, and there really aren't any definitions, but basically we just got to get right into the properties here. And so a couple of things that we need to know about logarithms. First of all, there is something called the product property of all logarithms, which says if I have log base b of the product of m and n, that becomes log base b of m plus log base b of n. So we basically take these two numbers, whatever they are. If I can write it as a product, then I can split it and make it log base b of m plus log base b of n. Now, it has something to do with the fact that when I have the same base, b to the m times b to the n, we would take b to the m plus n, right? And so these two numbers end up being added together. And so that's kind of the same idea when we use the log base b of the product of m and n becomes the sum of n and n, m and n. All right. Same thing here when it's the quotient. This becomes log base b of m take away log base b of n. And finally, log base b of m to the n. Basically, whenever you have this being raised to a power, we're going to take that power and slide it right out in front. So it becomes n times log base b of m. All right. So again, if m is being raised to a power, we slide the power out in front. All right. So what we're going to do here then is we're going to take a look at using some properties of logarithms. Now, we don't have any way to evaluate log base 5 of 4, at least not yet. We will here in just a few moments. But so they're going to give us log base 5 of 4. And again, please remember, this means that 5 to the 0.861 power is equal to 4. All right? So that's what that means when we go back to the exponential notation. So they're giving us this idea that the log base 5 of 4 is 0.861, and log base 5 of 9 is about 1.365. Again, these are approximates. We're going to use these. All right? So log base 5 of 4 over 9, again, because that's a quotient, becomes log base 5 of 4 minus log base 5 of 9. And since log base 5 of 4 is 0.861 and the other is 1.365, this becomes negative 0.504. All right? Now, this next one's a little trickier because what we do now is says log base 5 of 4 times 9. They were awfully nice about it because they gave it to you as 4 times 9. You know, again, this is now log base 5 of 36, and we can split that into 4 times 9 because those were the two numbers that we had log base 5 of. So it might seem initially like log base 5 of 36, well, I don't have a 36 here. But I can make a 36 by doing 4 times 9, and so that becomes log base 5 of 4 times 9. Since this is the product of 4 times 9, it becomes the sum of log base 5 of 4 plus log base 5 of 9. Log base 5 of 4 is 0.861. Log base 5 of 9 is 1.365. And so when I add those two things together, I get about 2.226. All right? Now the last one's probably the trickiest one. We have to think about 81 as a power. Now if you look up here, you've got 4, and I can't do anything to a 4 to turn it into an 81, but I sure could change a 9 into an 81 by squaring it, right? So really, this is log base 5 of 9 squared, because 9 squared is 81. So we're going to write 81 as 9 squared. Why do we do that? Because when I have log base 5 of 9 to the second power, we have to slide that back out in front, and this becomes 2 times log base 5 of 9. All right? So that's 2 times log base 5 of 9, which comes out to 1.365. And if I double 1.365, you end up with something around the neighborhood of 2.73. All right? So there's a couple checkpoint problems on the bottom. It's going to give you some values that you're going to start with. It gives you log base 3 of 2 and log base 3 of 8. Let's see if we can't do something with those. All right, so log base 3 of 4. Well, I don't have log base 3 of 4, but I have a 2 and an 8. I can't do much to an 8 to change it into a 4, but I can certainly write this as log base 3 of 2 squared because, again, I do have log base 3 of 2. Because that's given as 0.63. And so if I can write 4 as 2 squared, now I get to use that exponent property, the power property of a log, that says that this gets moved out in front. So it's 2 times log base 3 of 2. Again, by writing 4 as 2 squared, I get to make that 2 squared and then pull the 2 out front. So this becomes 2 times log base 3 of 2, which is 2 times 0.6309, which comes out to roughly 1.26. Well, we'll call it 1.262. All right? Now, log base 3 of 16, for the same reason, we're going to write this as log base 3 of 2 to the 4th power, because 2 to the 4th power is 16. Actually, we don't even use this one. That's kind of misleading because some of us might want to try to do something with that. You can do it that way. Suppose there's two ways to do this problem. We can then take this and slide it out in front. It becomes 4 times the log base 3 of 2. Log base 3 of 2 is that 0.6309, and 4 times that comes out to 2.523. Now, as I'm standing here recording this lecture, I realize that we could have also done this a different way. We can also write log base 3 of 16 as log base 3 of 8 times 2. All right? Because that's log base 3 of 8 times 2, this becomes, and I'm kind of running out of space here, this is now log base 3 of 8 plus log base 3 of 2. And so if I do log base 3 of 8, which I have, that's 1.89, and log base 3 of 2, which I also have, is 0.63. If I do 1.89 plus 0.63, I'm going to also end up with this 2.523 number. So a couple different ways you could have approached that particular problem. All right, so hopefully we got some variety there. All right, let's expand a logarithmic expression. Again, remember, this is log base 3 of 7x squared over y, and since this is a quotient now, we can do a number of things with this. So I guess the first thing I want to do is I want to separate the quotient into log base 3 of 7x squared minus log base 3 of y. Now again, we're expanding this, so when I get all done, it should be a much longer logarithmic expression. All right? Now this doesn't simplify anymore, but this first one sure does. This is log base 3 of 7 plus log base 3 of x squared, because again, this is the product of 7 and x squared, so I can split it into the sum of 7 and x squared. Don't forget I still have log base 3 of y on the end. All right? Now the last part of this is still log base 3 of 7. That doesn't simplify. Now, because this is x squared, we can pull that squared out in front. It becomes 2 times log base 3 of x minus log base 3 of y. Now again, that's a much longer expression than what we had to begin with, but that's okay. The purpose of this was to expand. All right, now going the other direction, let's condense a logarithmic expression. All right, keep in mind that if I'm taking 3 times this log right here, all right, 3 times this log right here says that this 3 gets lifted and puts back as a power here. So this becomes log base. Now these are all log base 10 because we don't get a number here, so this is a common log. They're not giving us a base. All right, so it's the common log, 3 times the common log of 3, and that means that we're going to bring that 3 back up top. So as I bring that 3 back to the power, we can comfortably go in between those two, hopefully. All right. Now because this is a sum here, this becomes the product of 2 and 3 to the 3rd power. So this is common log of 2 times 3 cubed, all right, minus log of 9. Again, because these are all the same base, this is log base 10, we're subtracting, that turns into a quotient. So this is then log of 2 times 3 cubed, all over 9. And now all we have to do is simplify this. 2 times 3 cubed, 2 times 27, all divided by 9. 9 goes in there 3 times, and I get 6. And so your answer is just log of 6. Again, please remember that because we're not seeing a base here, these are all common logs. This is log base 10. All right? So let's try to expand one of these, and let's try to condense one of these. Try the 2 checkpoint problems. We'll be right back with solutions. All right, this guy's quite a little bit here, but again, it's all log base 10, so we're not going to worry about writing a base. All right, so this is going to be log of 7y cubed minus log of 4x squared. All right, because it's the quotient, we're going to subtract those two, top and bottom, take the logs of each. So this becomes log of 7 plus log of y cubed, because again, 7y cubed makes a 7 and a y cubed. Now this gets a little tricky because we're subtracting this whole thing, but because this is 4 times x squared, I can write this as log of 4 plus log of x squared. And now let's deal with the fact that this was subtracting the whole thing, and so this is minus the whole thing, which becomes plus a negative and a negative. All right? From there, because this has a power of 3, we slide it out in front. This has a power of 2, we slide it out in front. My final answer is log base 10 of 7, or common log of 7, plus 3 log of y. And then this is minus log of 4, and then minus 2, because again the 2 comes out with the negative, minus 2 log of x. Now, we're condensing a natural log. Who cares that it's natural log? It doesn't matter. Remember, natural log is the same thing as log base e. All right, no big deal here. Because this is the sum, this becomes the natural log of 3 times. But we can't really do anything with that just yet. So sorry, I kind of took the wrong first step. Because this is a 2 here, we have to put that back as an exponent. So this becomes still natural log of 3 plus natural log of x squared minus natural log of y. All right, so the 2 gets moved back up top onto the exponent of the x. Now let's start putting some stuff together. Because this is the sum, now I get to say this is 3 times x squared. So it's the natural log of 3x squared minus the natural log of y. And because it's minus, that turns into a quotient. It's the natural log of 3x squared over y. There's your answer. All right? Outstanding. So we've been talking about this idea, going back here a little bit on our notes, we've been talking about this idea of not being able to find the log base 3 of 2. Basically, we're saying 3 to what power is equal to 2, right? Well, so far we haven't been able to evaluate bases other than 10 and e on our calculator by using either the common log feature or the natural log feature on our graphing calculator. So now we're going to get into this idea of something called the change of base formula. And the change of base formula does exactly what it sounds like. It allows us to use different bases when we go to take the logs of these various numbers. Okay? So this is log base c of a. And again, it says a, b, and c are positive numbers where b is not equal to 1. Basically, the base isn't 1. And in this case, c is not 1, so this number right here is not 1. So as long as that number is not 1, obviously 1 to any power is just 1, so it doesn't make very exciting logarithmic graphs, okay? So what we say then is we say, look, if I have log of some base, maybe c, okay, it could be a 5, could be a 6, could be something or whatever, all right? We can write this as the log of any base we want of a, log of any base we want of c. So it becomes log of any base we want a, log of any base we want c. Now, any base we want, why don't we use things like log base 10 or the common log or natural log, which is the log base e, right? So we can pick either log we want because we have the ability to evaluate those kinds of things, whoops, not that one, this one, on our calculator. So in particular, log base c of a becomes log of a over log of c. Now, what's the base if we don't write it? It's 10. And we do have a log base 10 feature on our calculator. It's just the LOG button on your calculator. All right? And so, and we'll get to an example in just a second here. We could change it to any base we want. Like I said, b can be any base you want it to be as long as it's not 1. So if I use base e, for example, well, then I can make this the natural log of a over the natural log of c. So the point is that it doesn't matter which log feature you use, you're going to get the exact same answer. All right? I'm going to do one with natural logs and common logs. So let's try this one. It says evaluate log base 6 of 11. What we're saying is 6 to what power is equal to 11? Well, as you know, 6 to the second power would be 36. 6 to the first power is 6. 6 to the second power is 36. So I would expect this number to be somewhere between 1 and 2. Probably on the low side, more like a 1.2 or 1.3 or something like that, right? Okay, so let's see what we get. Log base 6 of 11 becomes log base 10 of 11 over log base 10 of 6. Now, log base 10 of 11 ends up being something like 1.0414, and log base 10 of 6 comes out to something like 0.7782, which is something in the neighborhood of 1.3383. All right? What if I did it with natural logs? Instead of choosing log base 10, I'm going to use log base e, or natural log. So this becomes natural log of 11 over the natural log of 6. Now the natural log of 11 comes out to 2.3979, and the natural log of 1.7918 becomes 1.3383. Now, as I said before, 6 to the first power is 6, 6 to the second power is 36, so 6 to the 1.3383 power should be approximately equal to 11. All right? Now, let's plug some numbers in our calculator. Let's go ahead and spend just a couple minutes talking about evaluating this in our calculator. If I wanted to do the change of base of log base 6 of 11, I would do log of 11 divided by log of 6, and I would get that 1.338 number. Now, to test that answer, I would do 6 to that number and I should get 11 here, and I do. All right. If you want to evaluate just the log of 11, you can just do log base 10 of 11 to get that number. That's where I got the 1.04 number from before. And if I want to do the log of 6, I can do that same thing. You really don't need the end parenthesis as long as you're not doing anything after it. Okay? So that's where I got those numbers from. Let's go ahead and have you guys try a checkpoint problem or two on your own. Be right back with solutions. Okay, so this becomes log base 10 of 26, and I'm going to write the 10 in there just for now, just so you're comfortable with it. But again, this is log base 10 of 26 over log base 10 of 16. And this one, I'll do the other one with natural logs, because again, you can change to any base you want. Natural log of 13 over the natural log of 5. If you chose log base 10 for both, fine, totally doesn't matter. Just wanted to show you you're going to get the same answer. Okay, let's fly over here to our graphing calculator. All right, and so for the first one we end up with, let's slide this over here so I can see. Let's do the first one with log base 10. So let's go log of 26 divided by log of 16. And log of 26 over log of 16 gives us 1.75. So what we're saying really here, guys, is we're saying that 16 to the 1.75 power is equal to 26. All right, let's do a change of base with the natural log now. Let's do the other example here. In the other example, we're going to do this now as the natural log of 13 over the natural log of 5. What we're saying is 5 to what power is equal to 13. I'm not using base e, but I can use base e to evaluate. All right, so let's go ahead and do this with natural log. This is natural log of 13 divided by the natural log of 5, and I get about 1.59. And so going back over here, this is 1.59. So we're saying 5 to the 1.59 power is equal to 13. Now again, think about that. 5 to the first is 5, 5 to the second is 25. And so obviously the power is somewhere between 1 and 2 because we get 13. Okay, so that concludes our lesson on 7.5 on applying some properties of logarithms. Some big stuff in there. We talk about that change of base formula. We finally get to actually evaluate some logs, which is a really, really big deal.